Welcome back. Let's talk about differential calculus here. This is suitable for ordinary level and higher level students. And believe it or not, you know so much about calculus already and you don't even realise it, because differential calculus is pretty much centred around slope. And you did loads of slope when you did coordinate geometry. So let me explain. Calculus is a further study of functions, and we use functions to represent real life situations containing an x value and a y value. So the x value is changing and the y value is changing depending on where we are on that curve. And we use slope to represent this or to calculate with this. But the issue is we've only ever calculated slope on a line because that's the only way you can calculate slope. So when you have a cubic or a quadratic equation where you have a curve or a wave, you actually cannot calculate the slope. So we have to rejig it, and what we do is we find a tangent to that curve and we get the slope of the tangent, and you can see me drawing that in on my diagram now shortly. So when we're doing differential calculus and we find dy dx or f dash of x, we are actually finding a slope function for any tangent on that curve. That's what you're doing. That's what dy dx actually represents. So believe it or not, you know so much more about this than you actually think. Do you remember rise over run from coordinate geometry? You were essentially doing that just in a different way, from a function's point of view. We are just measuring the changing aspects of the function. We learn calculus in two separate sections. Number one, the actual differentiation skills, and number two, the applications of differentiation. So really and truly, before you go any further with this video, you need to make sure that your differentiation skills are on point. The best way to do it is to do lots of different examples and to learn how to use each rule that you have in your log table. From there, we're going to start with the applications. And in this video, we're going to focus particularly on turning points, maximum minimums in this video. So let's look at our first example. So find the coordinates of the maximum and minimum turning points of the function f of x is equal to 4x plus 4 over x. The minute you see turning point, maximum point, minimum point, you need to think dy dx equals 0. Let's think about skiing. When you are skiing and you're on the top of the mountain, what way are your skis pointing? They should be horizontal, which means that the slope is 0 at that point. And skiing up and down our quadratic and cubic curves help us to remember this. So at any turning point, we know that our slope is 0, which means dy dx is equal to 0. So we differentiate our function here. We let it equal to 0. We solve for our x value. And remember, our x value is the x part of that turning point coordinate. This ends up being a quadratic, and we get two values for x. X is equal to 1 and x is equal to minus 1. Now, what do we do with these x values? Well, they're just the x part of the turning points. We need to also find the y part of that coordinate. So our points are created from the original function. So we take our two x values and we sub them back into the original f of x function. 4x plus 4 over x. I sub both of them in. I get 8 and I get minus 8. So I've got two turning points. 1, 8 and minus 1, minus 8. Now, you do need to tell me which one is which. So if you think about a graph and visualize what it looks like, the y coordinate will tell you which one is higher up and which one is lower down. So we know that 1, 8 is the max and minus 1, minus 8 would be the min. Time to look at a second example. So we are asked here to find the turning point of the function y equals 3x squared minus 6x plus 4 and determine if it is a local max or a local min. You can see here we're dealing with a quadratic equation, and a quadratic equation only has one turning point. So again, the minute we see turning point, we know dy dx is equal to 0, and saying that the slope of the tangent of that curve is equal to 0 at that place. Let's get into it. Find dy dx. Let it equal to 0 and solve for x. Remember, x is the location of the turning point. It's the x part of the coordinate. You solve for x here, you get 1 x value. You're going to sub that back into the original function to get the y part of that coordinate, and we find that it is 1, 1. Now, is that a max or is it a min? Just because the y part of that coordinate is positive doesn't necessarily mean it's a max. So we need to do something called the second derivative test. Now you could also sketch it as well, but the second derivative test is fast, quick, and very accurate. So what we do is we find d squared y dx squared, that's our second derivative, and if the answer is less than 0, it's a max point. If it's greater than 0, it's a min point. So we do that here and we find a value of 6, which means that our turning point is a minimum turning point. Let's look at our third and final example this evening. So g of x is equal to x squared plus a over x squared, where a is a real number, x is a real number, and x is not equal to 0. So they're telling us that g of x has a turning point at x equals 2. So we're asked to find the value of a in part I and then show that it has no local max point. So it's not a maximum point. So again, remember, a turning point means dy dx is equal to 0. So the information we have is we know that at that turning point, the x coordinate is 2. So I use that information. I find g dash of x. I get the derivative of it. Then I sub in 2 and I let it equal to 0 because I know that's the information. The slope is 0 at a turning point and we know that location is 2. So I do a bit of moving around and I solve for a. So again, your algebra skills here are important, and these are the prior knowledge that you are bringing forward with you all the time. Now I'm showing you all the full workings out here so you can go through it bit by bit and remind yourself of it. Now that we've found a, we move on to part 2, and it says show that g of x has no local max point. Well, again, we're going to use the second derivative test here. So we are going to get g of x. I'm showing the first derivative and then I'm going to work to get the second derivative. You can see here that I have an a and an x that I haven't filled in. So I take my a from part I, which is 16, and I'm using x is equal to 2 because I know that's the location of the turning point. They're telling me it's at x equals 2. So I sub both of those in. I get a value of 8. Now, due to my second derivative test, I know that if the second derivative is greater than 0, it's a min, not a max. Don't forget to subscribe for more great videos and take a look at this video tagged here.